Hello, I hear you're a material science student wondering about this course and would like to familiarize yourself. I'm here today to talk to you about diffusion. There are three types of diffusions. The first diffusion is vacancy diffusion. In this, the microstructure has a vacancy in itself, and it is represented here. What happens in this diffusion is atoms in the microstructure then switch places with a vacancy, as you can see here, and it continues to occur all the time. The second type of diffusion is substitutional diffusion. In this, atoms of two different atoms start to substitute in of itself onto each other. This is usually used using a point vacancy as described here. The third type of diffusion is interstitial diffusion, and this is where you have smaller atoms, such as carbon, that go into the interstitials, such as in the iron microstructure, and prevent the interstitial atoms and the iron atoms from moving on each other. There are two laws that describe diffusion. They were both discovered by Adolf Fick. The first law is the steady state law, which is not time dependent. In this law, it reads, the flux, represented as J, is equal to the negative diffusion coefficient times the concentration gradient. Concentration gradient is the concentration at one point minus the concentration at the second point after the reaction. This can also be represented as mass over area times the time, even though it's not time dependent like this one. In this one, transient, this is directly time dependent. And there's two types. There's the type where the surface concentration is greater than the initial concentration, and there's the type where the surface concentration is smaller than the initial concentration. So you use these two separate equations to describe them. To finish this, you use your earth table functions found in your book to get the value of this, so that way you can determine the components in the concentration gradient. Alright, now I'm going to show you an example problem. In a steady state at 1200 degrees Celsius, a 1 meter squared sheet of steel is 1.5 millimeters thick and has a nitrogen atmosphere on both sides at 4 kilograms per meters cubed and 2 kilograms per meters cubed. Diffusion coefficient for nitrogen in steel is listed as 6 times 10 to the negative 11th meters squared per second. In this, we're supposed to calculate the diffusion flux and the mass of the nitrogen after 1 day. So in this, you have a concentration gradient represented over here. The gradient is going from the 4 kilogram side to the 2 kilogram per meter side. Because this is a steady state, as mentioned before, we're going to use Fick's first law. So, that being said, J is equal to negative D dC over dt. So, we're given our D right there in the coefficient of friction, the constant. So J is equal to negative, and then it's 6 times 10 to the negative 11. And then our concentration gradient is 4 minus 2 over, and the distance between them is 1.5 millimeters, or 1.5 times 10 to the negative 3 meters. But it's technically 0 minus that thickness, so you're going to have a negative 1.5 times 10 to the negative 3rd meters on bottom. And this is going to give you a flux. And that flux is 8 times 10 to the 8th kilograms per meter squared second. Now using this, we're going to again use Fick's first law and say J is equal to mass over area times time. In this, we're given 1 day, so T is going to be 24 hours, which in seconds is 56,400 seconds. We're given our flux and we want to find our mass. So mass is going to be equal to the flux times the area times the time. So in this case, our mass is going to be equal to the flux we calculated up here, 8 times 10 to the 8th, times our area up here, 1 meter squared, so times 1, and then times our time, which is 86,400 seconds. And we're left with a mass that is 0.0069 kilograms, or 6.9 grams of nitrogen. And that's it.